Hello, everyone. Welcome to the April 22nd edition of Math 135. Today, we're going to be talking about hypothesis tests involving paired differences. So let's switch over to those slides so we can take a look about what I'm talking about. Many statistical applications involve asking about what happened before and after, and how do I make some kind of conclusion about whether there was a meaningful change. So this typically occurs when you have data pairs that naturally occur in before and after situations. So there's some object you measure before and after a treatment. The key is that it is the same object or person before and after that you're measuring. Applied problems in psychology, sociology, sciences, business administration frequently involving studying matching pairs. For example, in psychology studies, they look at studies involving identical twins. Biology studies often involve studying plant growth on plots of land matched for soil type, moisture, and sun exposure. And business studies on sales of matched inventories are examples of paired data studies. When working with paired data, it's very important to have a definite and uniform method of creating data pairs that clearly utilizes a natural matching of characteristics. So let's look at an example. So here's a situation, a question you might ask that will involve such an experiment. Do active learning strategies decrease math anxiety? So the situation involves an introductory stats course. The math anxiety levels of the students are measured at the beginning of the course. The course utilizes various active learning strategies, such as working at the board, and then the math anxiety levels of students were measured again at the end of the course. This is an example where you would use paired differences because you take each student and you look at their score before the course with active learning strategies and after the course where they've seen these active learning strategies. And you want to know, did their math anxiety level change? That's the experiment we've been having you all as participants in for Summit P. So how do we know? What do? We take their pre-score, that is their math anxiety score at the beginning of the course, and their post-score, which is their math anxiety score at the end of the course, and you need to look at the difference. So one key thing that you need to remember as we do this is that we're going to be using paired differences. So we're going to be operating with data pairs, not just data values. So before we look at any calculations, we need to work out how to identify what are some situations which involve using paired differences. So I'm going to have a couple situations, and I want you to take a second to investigate each one and identify whether you think that this is an example of paired differences or not. All right, so you're studying the relationship between the median income of families in the United States and the median household price. Does it make sense to use paired difference? So take a second to think about this and identify what do you think it makes sense to use paired differences. Well, the answer is no. Although you're studying two things that involve money, and you can fix it by state, you're not really comparing the same thing. The median income families, the median household price, you're just not measuring the same thing. In order to do a paired difference, you need to be measuring the same thing each time, not just having the same units. So this would not be an example where you would use paired differences. What about this one? Tamiflu is a medication used to treat flu symptoms. It is a miracle drug. Does it help people recover from the flu more quickly? You take a sample of 100 students who have the flu. You randomly assign the students into two groups. You give Tamiflu to one group, and you give a placebo to the other group of students. In both cases, you record how long the students take to recover. Does it make sense to use paired differences? Well, now you've had a chance to think about it. What do you think? Again, the answer is no, because you don't have a pairing. The same individuals are not getting the treatment and the not treatment. See, that's one of the key things about paired differences is you have an individual, there is a pre-measurement and a post-measurement. And you can pair an individual with these two data points. Here you've got two different groups of people, and you get some data from one group and some data for the other group. Some people get Tamiflu, some people don't. And so this is not a case where you would use paired differences. All right, so how do we do such a test? What you're going to do is you're going to get a sample of n matched pairs, A and B, before and after, or D is going to be the variable you get when you take the difference between the two. And you're going to compute the sample mean of it, the sample standard deviation of these differences. If you can assume that D has a normal distribution or a mound-shaped distribution, then any sample size is fine. Otherwise, you really need the sample size to be bigger than 30. Once you've done that, you have some choices to make. You have to know what's the null hypothesis. Typically, we're going to pick a null hypothesis of no difference. That is, there was no difference in reporting between the before and after. In the context of the application, you're going to choose whether you think the difference is maybe bigger than 0 or less than 0. This is something you'll need to know from the problem. And then you calculate the test statistic, which is t. And you see that's done in the same way we've done it before. And the rest of the test should go like normal. Okay, so let's actually do one of these tests and see what happens. So we're going to do an experiment where we compare anxiety levels induced by looking at real spiders and pictures of spiders. See, we're measuring the same thing for each individual, their anxiety levels. And we're also measuring that each person gets 2 scores. Okay, so let's take a look. We're going to have a null hypothesis. And the null hypothesis is that there's no difference between the two. And what about our alternative hypothesis? Well, we're going to be taking the picture data minus the real data. And what might you think is possible or probable? You probably guessed that pictures produce less anxiety than real spiders. So the picture data minus the real data, you would expect to be negative. All right, now we need to compute the differences. So the differences are computed by taking the picture data minus the real data. Okay. Now, I did that by hand, but really you're going to want to do this with Excel. So let's clear all the drawings and go to Excel. So you can compute the differences very quickly in Excel by taking the picture column minus the real column and then dragging it down. So I need to compute the average of those numbers. And I need to compute the standard deviation of those numbers. This will be very important in my analysis. Okay, so let's go back to our whiteboard and start recording everything we have. So we knew that our null hypothesis was that there was no difference between the anxiety levels viewing pictures versus real spiders. And the alternative hypothesis was that we think that viewing pictures is less anxiety provoking. We took a sample of size 12 and found that the sample difference was -7 with a sample standard deviation of 9.8. So we need to calculate the t-value, and the t-value is our average difference minus 0 over the standard deviation over the square root of the sample size. In this case, -7 over 9.8 divided by the square root of 12. And let me see if I can calculate that using Excel. I get a t-value of negative 2.47. Now I want to calculate the p-value. So this is a left tail test. So I'm going to calculate the left tail area. And it's a t-distribution, so I need to figure out how many degrees of freedom it has. And it's always the sample size minus 1. So that would be 11 degrees of freedom. So let's go back to Excel. And let's calculate the p-value. So it should equal t.distribution of the negative 2.47 with 11 degrees of freedom, and we always put true. And that gives us a p-value of 0.016 roughly. A p-value of 0.016. That's very small. So what this is going to lead us to do is we're going to reject H0 and accept the alternate hypothesis. So let's go back to our slides to see what was it that we were asking to do in the beginning. We were wanting to know, at the 5% significance level, do we believe that looking at real spiders is more anxiety-provoking? Well, we rejected the null hypothesis that looking at pictures and real spiders is equally anxiety-provoking in favor of the alternative. So we conclude at the 5% significance level, that looking at real spiders is more anxiety producing than looking at pictures of spiders on average. This doesn't tell you what happens for an individual person. There will be people who think that pictures of spiders are more anxiety provoking than real spiders, but on average, we're convinced that looking at real spiders is more anxiety producing on average. So there was actually another way of doing this that was even faster than what we just did. So I brought the data back here onto Excel. And there is, if you go to data at the top, there should be a button that says data analysis. This is only on downloaded versions of Excel, and it's a little difficult to find sometimes. So I will help you in class find it. But if I click on data analysis, I want to do a t-test paired for two sample means. So I do that. I take my variable 1, I take my variable 2, my hypothesized mean difference is 0, my alpha is 0.05, and it does the hypothesis for me, and it gives me a p-value of 0.015, basically the same as what we got. And so this is a way of taking your data and doing a two-sample paired t-test automatically without going through all of those steps. So now you can interpret the p-value using this data output from Excel. Let me know if you have questions.